Popping bottles in the ice, like a blizzard. When we drink, we do it right. Getting slizzard, sipping scissor in my ride, like 3-6. Now I'm feeling so fly, like a G6.
So this is what we call the tangential acceleration. We didn't have that before because we had uniform circular motion where the speed was not changing. Okay? So we didn't have this AT. But if we're speeding up, if we have this alpha now, then we have a tangential acceleration. Okay? So now there's two components here of acceleration. Okay? AT is equal to the tangential acceleration. Vt was equal to r omega. At is just equal to r times alpha. So if you have one, you can get to the other pretty easily as long as you know the radius of that path there. It's easy to go back and forth between the linear and the angular variables here. And just from these equations here that we saw for the Vt, and now here for the At, the tangential acceleration here. Okay. We will see the same thing with the units one more time. That if you put your unit here of a meter in for that radius, and you put your unit here for alpha in as radians per second squared, you're going to get units of meters times radians per second squared. But this just has units of meters per second squared. Okay. Another time where you would just leave that radian off when we're going back and forth between the linear and the angular variables here. AC, we remember, is our centripetal acceleration. Anybody remember what that equation is? James, I think you know it.
Oh, I'm sure I don't.
There's a V in here. What else? There's an R. Does that look familiar at all?
Not really. It's been a while.
This is alphabet soup at this point.
Yeah, and that's part of what today will feel like, I think, because of all these things here. And this is the part that I really want to give you this quiz to look it over the weekend. And once you do it, you get comfortable with it. And it is for a while. And this is the part really with this part of the material in this next unit. Mistakes that happen with kinematics are usually mistakes because you're mixing up all these different variables. You don't know sometimes if you should call your A an A, a T, an AC, or an alpha. You put numbers in the wrong place. There's common mistakes that people make with just mixing up all the variables and not knowing how to translate the problem and take the numbers and then, do I know if I call that omega or a V? That's what I want you to start getting into over the weekend. It's just getting comfortable looking at all these new variables. Okay? So we have an AC and the AT. This was an old equation, but this is an equation that I do want you to have memorized for this test because we're going to be using it here in this unit. And for many of you, like you just said, it feels like it's new anyway. So let's treat this like a new equation and add it to our list here for this
No
unit.
problem there.
Okay. So we also have here, now you have two components of acceleration. Before, remember how we always chose our coordinate system to try to go with the acceleration? And then when I did that, I only had acceleration in the x or the y. When we were going down the incline, I just rotated my coordinate system so that one of my axes went with the a. We never had two different a's before. These two components here of the acceleration make up the total a, the full acceleration, which is just really a vector that does this. The AC and the AT combined is really just a vector that does something like this. That one we call A. A is just equal to AC squared plus AT squared. This is the total acceleration. These two vectors here are always perpendicular because one is tangent and one is toward the center. So that's why we can say here from Pythagorean theorem that your A is just the hypotenuse, really, of these two vectors if you're going to connect them from head to tail there. That's really just like taking ax squared plus ay squared, where these two here could be your x or y components of a vector. And they will always be perpendicular by definition here of tangential and centripetal. Those are always at a right angle. So we have three different a's here. A t, a c, and a. You have to make sure you understand that notation. Okay. With our v's, the velocity, there is no difference between a v, a vt, and there is no vc. Okay. There is only one linear velocity. That's v. We can put the t on there if we want to, like we've seen in the equations. The one here that I was talking about with the vt is equal to r omega. But this t right here, or that vt right there, is the same thing as the v right here. V is v, right? There is one velocity in meters per second. Whether I call it tangential or not, really depends on if we're actually rotating or not. But this is a v in meters per second. The t, the c, and the no subscript on all these a's really mean something. So just make sure you know that we have really here two components of acceleration. One tangent to the circle, one toward the center. Okay? And a is the combination of those both. That's the magnitude of your total acceleration here, which has components of the tangential and centripetal a's there. Okay? Any questions?
I think this class should count for a foreign language too.
Yes, it should. Which is why some schools don't make physicists take a foreign language, because they have so many other physics classes to take. But then there are some schools, and actually in the older schools, or just back in the old days, there were a lot of schools that would make you learn another language and translate a physics journal in that different language. So you might learn German, you might learn some other language, which was common for physicists here, and you'd have to actually learn that language and translate a paper and then give a presentation on it.
Wow.
As part of your degree. Thankfully, I'm not that old and I didn't have to do that. But most of our classical physics wasn't discovered in the time that we've been here on this country here, right? And this is all older stuff. This is classical physics. It's been around for a while and discovered by people that weren't here in the U.S. because we weren't here yet. Okay, so we did all of our acceleration there. I have all these on here. On this list here, we should also really know the difference between the AC and the AT. We need to have AC and AT here also. These all have units of meters per second squared. But there is no angular correlation here between the centripetal and the tangential. Okay. So we have centripetal and tangential for these A's, but nothing more over here to add to that list. I will probably ask you for this whole thing right here on Tuesday. So just know all of it. Know all your variables. Know all your units. For
All of it?
yes. I'm not guaranteeing I'll ask you all of it, but I'm telling you to know all of it so that you are capable of answering all of it. Okay, so after we did all this, we then went to the case where we have constant acceleration. For constant acceleration, we had all those kinematics equations that we can use for that case. So the ones like v is equal to v naught plus at. If I was going to write this in rotational or angular form, how would I write this equation if I'm telling you it has the same form here? What would all those variables turn into if I wanted to talk about the angular velocity, angular acceleration for my equation over here?
Omega.
Omega
Plus
is equal to
omega naught.
omega naught.
Plus
Alpha.
The fish, the alpha times time. There is no rotational time. All of our equations will have the exact same form. We're just going to put the different letters on there now to talk about all these angular measures. So we had one over here that was x is equal to x naught plus v naught t plus 1/2 at squared. We had v squared is equal to v naught squared plus 2a times your x minus x naught there. Then we had one more, like that. You should be able to write all these equations now in rotational or angular form over here. So what does my x become? X was position,
Theta.
linear position. Now we're talking about angular position. Those are just thetas now. So theta is equal to theta naught plus omega naught t plus 1/2 alpha t squared. And then same thing with the other equation, omega squared is omega naught squared plus 2 alpha theta minus theta naught there. And then the last one, looks like that. Identical to what we've seen before. All these relationships here. Your velocity is just the rate of change of your position, like we saw before. Your acceleration is just the rate of change of your velocity. These are all just new variables now. Okay, so we've got these equations. Do you guys remember what we did every single time we were going to use kinematics and use these 4 equations? What list did we make?
Anything new?
The
I don't
Yeah.
think so.
All the variables that are in these equations, because then once I look at that list, that would hopefully help us choose which one of these would be most useful. And so, when you're doing these problems, we'll do the same thing like we've done before. Make sure you kind of know where your initial and final is, and then just start setting up your equations based on this list of variables here. Just like we saw before. Set that up, and then choose one of these equations. So anytime you're accelerating, you use these. Those average equations that said delta theta over delta t, or delta omega over delta t, you don't use those unless I ask you for an average. So be very careful about when you're using your equations, because some of these problems will feel like unit conversions. Like you're going back and forth between radians or revolutions, and you might just feel like, well, if I have radians and I divide by time squared, I might get alpha. Don't do that. Use the equations when you have them, and when you know you're accelerating, just stick to these and trust these. Don't just say, well, I think I should divide distance by time, and that'll give me velocity. That doesn't always work. Okay? And that didn't always work back here when you did kinematics either. When you're accelerating, you can't do that. Trust what you're doing. Okay? You'll be able to use these just the same way that we used them earlier on this semester. I will probably ask you to write these down on Tuesday also.
oh, what was that last one?
Here.
Did you miss one?
Yeah. Moving a little slow.